Okay, it's about time, so good morning to you who decided to come here this morning. Well, let's start the lecture so we get things done. We have quite a lot of things to actually talk about because this lecture is sort of a recap on the first week's topics and also talk about several new things. I still like to remind you that we are recording these lectures, so if there's anything you miss during the lecture or want to hear the explanation of some aspect, then just go to the internet and to Noppa pages, and from there check out the course recordings. Anyway, this morning we'll start with the revisitation of the topics from the first lecture. On the first lecture we were talking about topics such as what is software engineering and what actually is software development. But one thing we actually left out on the topics was the fact that beyond software engineering there's also the aspect of information systems. Of course, since last week you had the lecture online on software processes, the information systems might be somewhat confusing aspect. Well, anyway, let's take a couple of slides on this lecture to talk about the difference between software engineering and information systems. Of course, the software engineering, like mentioned a couple of weeks ago, has basically two sides on it. The one is the development of technical artifact. That's the software, games, all the other things that we are actually programming or designing and testing later on. But there's also the software development as an industrial activity, the development process and act of managing people or doing the software and to fulfill some requirements. So I have to close the doors because that woman there is juggling with the kitchenware. It's kind of annoying. So let's try again. Yes, so there's two sides on the development. The software engineering as a development of artifact and software engineering as a management of software process. So overall, if we consider what are things related to software development, there's business aspects, testing, quality aspect, project management, software architecture, design, development of documentation, training work, programming work, and all these other things. Basically saying that if you talk with software engineer or someone who's doing software engineering tasks or software engineering research, it may be completely different than what you think about. Development of documentation, document creation, management, development of training material is something that falls into the category of software engineering and software development, since we have to have users who are able to use the software. But on the other hand, also the programming work, something like optimization of the applied search algorithms, is also something that's software engineering. So overall, considering some example topics of what software engineering research, for example, is a really good illustration on the fact that the things related to software engineering and overall the entire area of software engineering is rather huge. For example, how should programs be made? What sort of aspects are related to programming languages, compilers, and tools? This is something really technical and something that really requires certain skill set and experience, for example, on compiler construction. On the other hand, we can also have things like what are good software testing practices, what is software quality, what are good structures in software, that like design patterns and stuff like that, which are more or less on the more creative side in the work. Similarly, going into somewhat farther from the development work, also aspects of project working. How to enhance group work, how to manage a software project, or simply in business, how to be successful in software development business. These are all some areas of software engineering research. Okay, so what is an information system then? We know that software engineering is a huge collection of different topics. So what is information system? Well, the information system is the larger context of managing information. The information system is the entire ecosystem of managing data or managing information, where software is only usually the tool applied to do the data management. For example, there's a couple of formal definitions. Information system consists of people, processes, data, models, technology, and language forming a structure which serves an organizational purpose or a function. Or system which assembles, stores, processes, delivers information relevant to organization or society in such a way that the information is accessible and useful to those who wish to use it, including managers, staff, clients, and citizens. An information system is a human activity system which may or may not involve the use of computer systems. So basically, it means that the information system is the larger concept which has people in it, language in it, social and organizational aspects in it, and human activity. The software is only one part or one component. Consider it like this. The library as a concept, place you can go to borrow books or read stuff, is several thousands of years old. One of the first known libraries was the Library of Alexandria, which existed in Egypt around 2000 BC and it definitely worked as a library. They had the scrolls, they had the people, they had the language, they had the society or organizational aspects to manage that library, but they did not have computer there. No, well, they probably didn't. But they still had some way to manage all the information in their library. All the scrolls had their own places. The librarians knew where the system was, where each piece of information was, or who had loaned the what and who was reading what. And this also enabled people to find certain information from the library. So considering that today there are still libraries here, and we now have library cards, we have electronic systems which remember to bill us and do all the manual labor of the librarian, but still the software or the software and hardware tool we use on our university library is just one part of the entire information system that is the library and its management organization. Similarly with the airports. The first commercial airport opened before the Second World War, actually right after the First World War, and they still managed to organize all the flights and do all the other necessary things. And if you go to airport, for example in Helsinki, you have all these huge systems to just give information on to which gate to go. Is your flight cancelled or is it late, or other things. And the most spectacular part in that information system which the airport has is that it actually gives you information almost with no connection or requirement of having some cultural background. the same symbols, the same notation is used almost everywhere in the world. And it doesn't matter if you are in the airport in Helsinki or in Moscow or in Johannesburg or in Miami, you still get the same information from the same system. So that's one of the examples of better information system existing. It's actually so refined that it more or less has its own language. It's the simple language, arrows, graphic signs, that sort of things, but it's still an information system. Okay, so, well, we are dealing with people here, especially with information systems, because the people, the users, are one aspect of the system. So, the information systems have problems. Of course, there's, change resistance, and the people may sometimes understand same things differently. Also, the information system design is something that tries to get all the positive benefits to our organization or the users while trying to get rid of all the problematic areas. For example, if we manage to create information system which people like or actually start using, or which doesn't have the cultural problems or anything else, that's basically saying that the working and good information system enhances the work environment, enables the success of the organization, and it reduces the costs. So basically that's one of the reasons why people tend to create new information systems. That's actually also one of the reasons why software systems are upgraded, or people try to create better and more refined systems. As for example, the ticket reservation system used by the National Railway Company. We have had fairly sophisticated system which allowed us to buy tickets from online even 10 years ago, and still there was the requirement that, okay, we might want to upgrade this system. The upgrade project was more or less a spectacular failure at first because the new system simply didn't work. It assigned seats on train carriages which were not actually connected to the train, sold you tickets which you were unable to ride, and otherwise was a bit of a problematic system simply because it lacked stability and usability. So why did the National Railway Company decide to scrap their entirely serviceable existing system to replace it with something that was, well, let's say less than adequate on its quality? Well, the reason is simple, because they tried to reduce costs, they tried to introduce new features into the system. Now that we actually have the new ticket management system somewhat functioning, it's much more convenient because it allows things like electronic tickets and all these other things, which of course are used to, well, enhance the easiness of traveling. You don't have to print out your tickets anymore. You just show them from your mobile phone. The mobile site allows you to buy and pay your tickets from the mobile phone and these sort of things. Things that the older system could not do. Basically, new services that might not have been required at that particular time, but since the new services or new modes of services became available, they were something that the customers liked to use. For example, you really can't lose your ticket if it's in your email, in your mobile phone. Well, you can lose the mobile phone, but that's, well, a completely different thing. So, finally, what then is the information systems research? Well, Of course, the development methods, description languages, process models, risk management, development failures, development organizations, success factors, success in deployment and adoption, computational models, information systems as competitive factors. So basically, interestingly enough, unlike the course name, which is software engineering methods, we are actually talking about the information systems, simply because also the development work and other things related to the design, for example, gathering the requirements, are something that goes into the domain of information systems. Why our customers are using the software, how should they be using the software, what are the requirements that the system has to be able to do, or features or the system has to have, so that we can actually have customers and we can say that our software was successful and we can say that the project wasn't a failure. So, okay, so going to the final words about the software development, there's a slide missing in this presentation, but then why do we have to define these different methods of how to define a software system, how to create one? What is information system? It might be, for some it might be simply that, okay, this is just a course on management. Well, it kind of is. We are talking about management aspects here. We are talking about project management and other things related to development of software. But why do we need to understand how these methods work? What actually are defined by a software development method? And it's more or less mentioned here. How development is done, what tools and techniques are used, what is good and why. For example, we believe that if we put people work in pairs, we get better quality from our final software, which then shows it as an improvement or enhancement in our information system that we are trying to create. So, definition of why we are doing this, what's good for our purposes. For example, on the net lecture, online lecture, there's an example of extreme programming. The extreme programming, the XP, doesn't actually believe that we have to prepare for everything. We have to make comprehensive design, we have to make comprehensive architecture, because the extreme programming more or less relies on the fact that you first design your first draft. You first design something that answers your problems, and during your development work you get constant feedback from several sources, from several levels, which you can then use to refine your design as you go. So not only is the idea that you get your first implemented feature early on so that you can start doing testing work, you also don't prepare for every possible problem, but just try to steer away from those risks or problems that actually materialize during the project. That's belief on the behalf of the defined development method. For example, the rational unified process, or some more strict waterfall kind of approach, design first approach, says that you have to identify the risks so that you can actually understand how probable it is that you have problems, or you have at least some well-prepared plan if some of the most dangerous or problematic problems become reality. Of course, what's good preparation and what's overdoing it compared against what's just not caring about any problem. Also, similarly, what roles exist, what phases are included, and in what order. The phases are more or less self-explanatory. In the waterfall, you have sequences of different things like gathering requirements, doing design, doing development, doing testing, and then deployment. On the Scrum, you more or less gather the requirements similarly, and you do also do the design somewhat similarly, but during, for example, the development and testing work, you are doing short iterations which interleave testing cycles to development cycles to revisitation of existing parts or refactoring existing modules and code. These things are, well, more or less just ideas of what enables us to do good software engineering work, which leads to good software system which serves a usable information system. So finally, why then are these methods used? Of course, this course wouldn't exist if this would be just some random rambling by one person who has been working in the software industry, but usually the idea is that if we have roadmap into the development or have sort of instructions or like a recipe on how to do the software development work, we might have a reduction of complexity. We actually are able to manage our project and have some sort of control. We are able to review things. We kind of know where we are. For example, if we need to hire more trainees, or if we have to get more testers from our game, or that even we know that we will have something that we can launch or deploy at the end of the year. Because we know that we have these and these features we have to have, 50% of them work, 40% exist, and the rest 10% of the features are rejected. So we know when to go, for example, from the development work to the system testing. Also, the division of labor. So we know when we need developers, we know when we need testers, we know what we have to organize, and the people doing the development work at least have an idea what they are going to do next week. So this one practical example or one practical reason why this division of labor is important is that, for example, some test environments, for example, mobile phone network servers or mobile phone systems are really complicated things to create within one laboratory. So we may not have enough test suits to give one to each tester. We might not even have enough testing facilities for each project in one larger company. So these projects have to compete for those testing resources. So of course, if each project would just come and go to the laboratory, it would be complete chaos. But if we are able to manage and control our activities, we can work with less than ideal resources, leading to savings, which also lead to happy share owners and happy investors. Of course, it's also something like systematization of development knowledge, meaning that the brain drain won't happen in your project. The brain drain means that all the people who are very professional or experienced or have knowledge about your platform, experts on their domain, are hired to another company or have an accident or anything like that, and the people who know things just leave your organization. The way that you can't contact them later, either they don't care about your organization anymore, or that you can't reach people who are dead. So you use the systematization of development knowledge, meaning that you more or less document things do systematic training or try to keep all the people up to speed so that there isn't one project manager or quality manager who's the only person in your organization who actually knows about stuff. Others are just following one person's orders or one person's instructions, and when that person ceases to exist in your organization, then your entire process model just completely collapses. So documentation of work, management of this documentation, training work, all these other things which ensure that your organization isn't in risk of failure when one person decides to leave or has to leave the organization. Finally, for the rational reasons, it's the standardization of development process. This also is something that's, well, thing that you wouldn't think at the first round, because of course me telling you here how software is developed in the industry is the reason. The reason why this works is that because there is standardization. The companies follow certain patterns in their development. They use certain tools. They aim for certain platforms. So I can just pick the most common platforms, pick the most common process models, and pick the most common ways to do development, or pick the most common problems these organizations have and tell you about it here in the lecture. It means that you may not be already proficient software system engineers for Philips or Sony or anyone else, but you at least have the basic information. Since you know the systems, you know the process models, you know the different ways the software is developed, so it's easier for the organizations to get you up to speed with the development work than just trying to train a person from ground up. Okay, so of course, since people are also sort of mean to each other, also tend to lie and use the different things for their own political purposes, there's also the hidden motivation. That's one factor. It's more or less the negative side of development work, or why someone would try to force their new and great model into organization. This is usually the reason why the different process models fail. There's a long time running cartoon over the problems of engineers in a software development organization, and actually in many occasions the reasons why those problems exist in the first place is something from these. For example, the people like to professionalize their development work. It means that they think that if we take this rigid process model and force it upon everyone and make everyone work like we were in an army, it would make our quality soar high into the sky. Also, it means that if we professionalize or use some rigid model, it gives the developers, who usually are on the lower levels of the administrative ladder, some way to influence or get more power in the strategy formulation, meaning that the developers gain more power in the organization. Also, if we aren't quite certain that we are professional enough or good enough or our quality is good enough, using some method or model is the comfort or confidence factor that we are doing things properly. Of course, there's a saying that we can use more time making the system audits and making things properly, or the practice, trying to create proper practices, than actually doing development work. Because, of course, the only measurement in software project is how much we have progressed in our work, how much it costs, how much time it takes, and how good the final quality is. All these software process model, software development method, proper practices, things more or less don't work if the organization doesn't support that work. Also, if we are doing something which has legal consequences like development of medical devices or things like that, it also, these systematic approaches use the audit trail for protection against wrong decisions, and even sort of show that, okay, we made the best decision available. So overall, there's several reasons why people tend to adopt these different models, but usually the only way to make anything work is to see your own organization and try to modify the model so that it fits your organization, not the other way around. And for example, the ISO certification, which is a sort of a medal or prize for doing something so that it fulfills, for example, the testing practices of ISO IEC 29110. It says only that your organization seems to be doing things this way. But of course, if it's completely unnecessarily huge and large and demanding standard, the first thing your organization will do when they are running out of time or money is that they throw out all the unnecessary documentation work and all the unnecessary process model parts which aren't functional. So the few of these reasons may come from the, let's say, the decision or the need to do the right thing, but actually, usually these hidden motivations, the professionalizing your work environment or getting audit trail or creating ISO certification leads to the situations where your work ends up being a joke of the day in the Dilbert comic. Anyway, this first 30 minutes was about the things related to the first and the second lecture. So now that I have only spent about half of our time today, I'll start about the topics today. So today we are going to talk about the objects, UML, and requirements. Today's topic first starts with the discussion about the object-oriented programming things. Why things are designed as they are, what should you expect from the design, and then we talk about the UML, how it connects or how it is integrated into the design of different modules or objects. And finally, the last topic on which we will continue next week is about the requirements. So what sort of problems there are with the requirements, and how should the huge amount of information collected from customers be used to create something sensible. So first, what is software? These are the slides from the first lecture. So the software is a system that's composed of components. The components are inside in the software meant to do something like manage the network connection, listen the touch screen, or listen the keyboard pressings, or do some complex calculations. But overall, the software is composed or compilation of different components which send messages to each other. Within each component, there's a number of objects which are more or less the things designed with class diagram, or represented by class diagrams, and written on a programming language and then compiled into a source code. So finally, when we have functional system, we have software, we have database connections, internet connections, keyboards, touch screens, gamepads, mouses, heat sensors, all the other things, and the components inside the software have objects which more or less do all the heavy lifting work. So, then we have programming languages. We have the object-oriented programming languages, which we aren't going to be, talk about on this course, but which are topic of, for example, the object-oriented programming course, quite surprisingly. So there's messages, there's inheritance, polymorphism, abstraction, the use of objects, and of course the different object-oriented technologies. So we know that we are using programming languages to create those components and those modules which are then used to create the software to fulfill certain purposes. So, of course, these are the basic things. So, if we talk about class, we are talking about some entity which has name, it has attributes, and it has services or methods available. So basically, it's one set of things. For example, here the class dog says that one dog, for example, has a name, it has age, and it can bark. Well, if we are talking about object, we are talking about thing that has identity, privacy, and state. It means that object is something that we create from class. For example, the Fido here is object created from the class dog. So when we design a class diagram, we more or less define what sort of objects our software will have, and the objects then are they are unique, they have identity. They are, for example, all the customers in your customer database, or all the active connections of your server system, and so on and so on. But the class is something that defines what sort of objects we need on our system. So the objects react to messages. Like on the diagram shown, which defined that the objects and even modules exchange information, the objects are designed so that they send messages to each other. One, for example, customer can, or the account information, the class definition here on account, it has customer name, it has, or customer object, it has account number, account balance, and the interest rate of this particular account. It can get different sorts of messages, like deposit money, which adds into the account balance, withdraw money, or get balance, which do their obvious works of decreasing the balance or getting the balance to see if there's enough money in the account. So basically, what it means is that when we create the object to our software, we then expect that that object will get certain messages from other places or other objects, and then things will happen. For example, the objects like ones here can exchange messages so that there's the user interface, in which the user inputs one number. There's the control system that reads the input, and based on that creates the message which says that get balance from this account. Of course, there's data retrieval activities or even identification. The account then asks something from the customer object and then there's exchange of information so that everything works quite nicely. So everything is in their own little object or pod doing their things, and when these things work together, then we have activities. So then why am I talking about object-oriented programming topics here? I can see from your really interested looks that there's somewhat confusion over the topic of this lecture, but do not fall asleep yet. There's actually relevant stuff related to this. So the idea why I'm talking about the objects here is the encapsulation and information hiding. Because the amount of information in one software system is huge, it's also it's also a feasible idea or a promotable idea to only show the available information. It means that if you are working somewhere in the software, or you have one module in your software, that module should be able to only manage its own information or get access to the information that's relevant to its functions. That is, well, the reason is that since we have so many things like variables or different interfaces or protocols and things like that, we tend to have problems if we are doing maintenance or upkeep if we have several things referencing to several places. This is also the reason why global variables are not used or are at least very much hated in the software development work, because they make the later maintenance and system development work or creating new additions painful experience. So the encapsulation means that each of these objects should have their own well-defined work, and they are just doing that work. The related concepts cohesion and coupling mean that the cohesion is the definition of the extent to which an individual module is self-contained and performs single well-defined function. It means that all happens within one object, and if we want to replace that function or that functionality, then we just take that object out and replace it with something that performs the same function but more efficiently. Like with the car engine, if we want to have more power in our car, we might want to change our air intake or carburetor or whatever, add new chip on the engine control unit to get more power out of the system. That's really good cohesion, because the system is so well contained that just by changing one part, the behavior of that particular part is changed forever. So basically, it means that the high cohesion in software engineering means that the module has focused responsibilities, whereas low cohesion means that the object is something like a catch-all part, which does a bit of everything here and there, doesn't have the really one defined responsibility, or has several responsibilities which are more or less not related to each other at all. On the other hand, the coupling means the degree of interdependence of modules. It means that if there's high coupling between two modules, the modules need each other to the extent that they simply cannot function without each other. So if we want to replace one object, it may have hidden coupling with another part, meaning that if we want to refactor one part of our source code, we have to take into account something completely different. For example, if we have an object that does sorting algorithms for anything basically, it probably has high coupling with all the other parts of our software that rely on the sorting algorithm to give them the correct answer. It also means that if we have a high coupling, the module modifies or relies on the internal workings of another module, meaning that it has direct access to the internal variables or things like that. Whereas with the low coupling, we have set interfaces that everything works. And everything works more or less like we have documented things. So the reason for why I'm talking about the high cohesion and the requirement of low coupling is that the encapsulation is one of the things that actually are very much required when we are developing software. It means that we have, like in combustion engine, we have different parts that do different things, use the other parts as if they need their services. For example, they use the printing algorithm or database. A writing algorithm uses the sorting algorithm or sorting module by calling it and then sending it its data there and then getting back sorted list. And the parts are dependent on each other, but they are still separated enough so that we can replace one, like do maintenance or repair work or fine-tuning or whatever we want to, and still know that if we replace one part of the software, like get new, better algorithm for managing the user input from the gamepad, and so that we get more crisp and hands-on feeling on the game, then we know that we don't accidentally break anything. So basically, the idea with the object-oriented programming work is that when you start to do your design on technical level, you should design your objects so that each object has a certain function. There should be no objects that simply exist because you want them to be there or because the lecturer wanted you to have some control object in your system. So try to avoid the unnecessary complications and complexity, simply because the software should be designed like a car engine. You have parts, you put those parts together, and then you have something that works. So this all is related also into the talk about generalization, or more or less about the design patterns. I'm going to go through these more object-oriented programming-related aspects in quite a hurry, because they are something that you should keep in mind, but they also are something that should at least be talked about on the more programming-oriented course. So if you know inheritance from C++ or somewhere else, in the UML, the same thing basically is the generalization. You have superclass, for example, definition of car, 4 tires, 2 doors, engine, and then you have the generalization of that class, which means that you may, in a new class or inherited class, define something like sports car or van or truck or things like that. So that particular connection between things is shown with this sort of an arrow. These all symbols function in all diagrams. So if you have the definitions which are drawn like this, it means that there's a generalization in use. Also, it means that you can have this problem with the generalization. So you may have print in several places, but also it may mean that you just call print function somewhere, and the message doesn't care about how the printing work is done, as long as it produces the certain type of output. It also means that if you design something which has the student information or the invoice information or Word documents in your information system, if you define that, okay, everything has to be able to be printed, then you can just design a new print function for all these different classes, even though they are generalized, because you can override the data. So more or less the idea is that you can have the model which includes classes and relationships, and real world which has the concepts. And of course the object-oriented design thinks that well, you should be able to define your world, for example this classroom, by just setting things or defining things like they are in real life. Of course we know from programming language that this may not always be the right case, but still it's something that's comparable. For example, with the concrete real world, we have events or things or phenomena like this lecture here or your chair in which you are sitting. And in the model, for example, for this room, we might have a list of participants which are assigned seats, and all the seats have their own connections to the day they were bought or the day they were maintained or things like that. So basically the idea is to design the classes around the concept of real world use. So the abstraction, well, consideration of essentials. Leave out things that are not used. Try to find out the things, for example, for your database model, the things that you really need to have. Form the general concepts and then create the class definitions. For example, there's some things like the classification or individualization means that if you have a car, then you can add like the manufacturer's model number or registration number or different specializations, for example defining sports car instead of a car. So these are all more or less object-oriented things. So the slide I'm looking for is not on this lecture set, but well, anyway. So these problems, or the way to define different data models or create different functionalities for your software. For example, if you define all the network activities to go through one object, it means that you have an object that's more or less the network handler. Or if you have one object that listens to keyboard or listens to user, it's something that's always responsible for getting the user inputs. And well, there's some list of programming languages which more or less allow us to define objects so that we can use the real world or this high cohesion, low coupling thing as a basis for our design. There's a Java, C#, C++, Python, more or less most of the more modern high-level languages. So how does this then is affected to the unified modeling language, the UML? The databases and functional models did not correspond to each other. In the 1980s, there was the problem that the conceptual database model and the functional model were not designed for each other. For example, if we wanted to save or change our student information, we could create the object model which said that we have students. All the students have names, student numbers, list of courses they want to register, and so on and so on and so on. But when we use database program, there might be some problems with the relationships of different sorts of information. So basically, we had to design to do things separately. So also, there was gap between the requirement specification and designs simply because there was no one way of defining all the necessary parts of our software. Meaning that the situation was something like with the car industry. Every time you design a car, you also have to design a new type of screw for the work or create new type of blueprint, and every time one worker or designer goes from one car company to another, the designer would have to learn the entire new way of defining the blueprints or defining how the car would be manufactured, simply because the computing power and the capabilities of computers were so much larger than the earlier periods that there was actually a problem defining software that would be capable of using all the computing power or fulfilling all the purposes, while at the same time being somewhat systematically defined. Of course, there were several different strategies, for example, use case cards or some flow charts on how different events happen, but the UML more or less was designed because there was need to have one way which could be usable by all the different people in the industry. So the UML started with this idea that there should be classes, they should be objects, because they can extend to cover any domain ever. If we are trying to define a language or some sort of a design notation that can be used in electric design, can be used in a bus stop system design, or can be used to create some sort of register for cars, then of course there would be several different concepts which would have to be explained. So the idea was that, okay, we use these classes and objects and their messages and the way the different objects offer services as a independent system, like modules, or with the high cohesion and low coupling. They offer services and response to messages and are defined by classes and objects. Also, by using the abstraction to get rid of all the unnecessary details, the UML was defined to be able to be used as a design notation for any software domain on any level with any programming language and with any approach into software development. Whether you use Scrum or Extreme Programming or Waterfall approach, the UML would be something that could serve your business. So, the benefits of the object-oriented approach were also in case that the class diagrams, for example, could be further extended later. So consider that you first design something just to get a draft or idea for your programmers or developers, to get the idea that, okay, we have students, we have server system, we have network interfaces, we have this, we have that, and just connect them to each other with no consideration of how these things are actually done in a technical sense. With the use of class diagrams with the UML, the positive aspect is that we can just add new things. We can make more refined design, and we can add new things or more layers into the design, so that we have the abstract design, then more technical design, and also, for example, people who are in marketing or people who are in management or people who are working with customers, we can leave out all the highly technical parts. We can just get the abstract things shown, like deployment diagrams and things like that. Because, well, the customer really doesn't need to know how our server-side system architecture is built. They are more or less interested on the fact that, okay, we are going to do this server here, put the web interface here, and that sort of thing, and do that sort of things. So that's what we got with the UML. The notation language, which is extendable enough to define any problem, and language which uses the object-oriented approach. So the UML is more or less global industry standard today. All the major companies, Siemens, Microsoft, etc., what was Nokia, were all users of the UML. I would be lying if I said that it has wide use in the software industry. All the major companies are committed, meaning that, or that it's a global industry standard, means that if some formal design language is used, then it's usually the UML. But of course, there's also the problem that not all companies use any sort of design language. So the idea is that the UML supports the whole life cycle from requirements to deployment, meaning that you can define anything from the first discussions with your customer or collection of the requirements to the final days of development, getting your work to the app store or delivering your work to the customer. It's also, well, yes, it fits to the most application areas, and actually it has good tool support. For example, the Star UML or Argo UML are completely free tools, and for example, things like Microsoft Visio is completely capable of drawing you UML diagrams. So you don't even have to buy any special software to be able to draw the UML diagrams or do design work with them. If you are running a larger industry company or doing something which involves large amount of people, there's also process models which are directly aimed to using the UML language. So the UML has following things. The UML has the class diagrams, the use case diagrams, sequence diagrams, collaboration, state chart, activity, deployment, component, and object diagrams. These are from the UML 1. These are the first ones which were designed, and later the UML 2 notation added things like timing diagram for getting more information, for example, on something like anti-lock brakes, and changing some names to communication diagram or composite structure diagram. Basically, these diagram types are all meant to define things from the different perspectives of the software. For example, the class diagram, as shown here, is more or less the definition of the different concepts of the system. For example, here it defines a company which has office, which has departments, and those departments have persons, and they have contact information, and so on and so on. So there's different sorts of connections or relationships which are defined more in more detail in the internet lectures or the course video archive. You should go check them there. But the idea of class diagram is that it starts as a really crude, high-level, high abstraction model, which is then extended or more details are added, for example, by applying the boundary control entity analysis, in which the actual technical considerations are taken into account. The class diagram is the high-level representation. If we want to go more into the detail we can use component diagram. The component diagram describes the physical structure of the implementation. It shows how the system is divided into the components I talked about earlier, and it sort of shows the architecture of the system, meaning that this level shows the actual division of the software into functional components, or things that we can change, or things that are doing something for the entire system. Of course, the network of components then defines how the entire software is built. The next one goes even more into details. That's the composite structure diagram. This is something that I have never seen in use in any software organization. This goes into the fine details, actually defining what are the different variables, what are the variable types, and what are the different functions or function calls within one object. And this isn't really that much used. But if you want to go in even inside into one component or even one object, and then you can also model classes, internal structures of classes and their interfaces. Of course, not all the diagram types are meant to be used for definition of programming structures. For example, the deployment diagram here is more or less the description of how the system's hardware is arranged. So we have more or less the basic internet service here. We have user who's sitting on their workstation using web browser, which is running in the workstation. They have connection over the HTTP connection to web server, where we have a web interface and database system with log file, and the entire web server is connected to external database, which fetches data from MySQL database. So more or less the definition of that. Okay, these are the parts that your system will be built on, and these are the places we will deploy your software. It's something that defines or describes how the system will be installed. Of course, more into things about programming language, object diagram can be used, for example, to show how the different data models work. These are just, for example, information connected to one person or department, examples of how the data within the system is connected to each other and what sort of relationships there exist. Package diagram is also usable. It shows larger blocks, and it's more or less the filing structure of the UML, meaning that you can organize your things, your diagrams, your use cases, your requirements, your source code into these packages. So for example, if we want to have someone working on this module about students, they can just get all the information about that module there, and they can also see that, okay, I should have no connections to the module handling the data about professors, right? Because it's just that they are connected. They aren't connected to each other, so any editing work or refactoring work I do with the student module doesn't affect the staff module. Then there's more, let's say, more marketing people-friendly diagrams here. The activity diagram actually doesn't model anything about the system structure. It's more or less a diagram which shows how things happen within the organization. For example, how user would start their game console and start their game. Put the disk on, start the game console, wait for loading, check for updates, etc., etc. Also something like how contract is made. Like here, select site, commission architect, develop plan, bid for plan, then there's accepted, not accepted branch, parallel activities, and all these other things. Also could explain something like how post office sends one package from one company to another. There's a person delivering the package to post office. The post office identifies and categorizes the package, sends it to the logistics center, they sort it out, and all these other things. Also, if we have parallel activities like how billing work and package warehouse work happens, so that nothing is sent out from the warehouse before the customer pays their transaction or things like that. These can be defined with the activity diagram. And well, the state chart diagram is, I guess, it's familiar for people from the computer science industry. If we are designing something really close to embedded programming, like a remote control or things like that, or elevator management system, we can use state chart to define the different states and different transitions from one state to another. This is also really closely related to the actually how the software system functions when it's online, whereas the use case diagram is more or less just collection of different stakeholders, which we have been already talking about on the exercises, and how these stakeholders use the system, definition of use cases, so to say, what things we have to be able to do with the software or the system. For example, place phone call, receive phone call, use scheduler, and also there's use cases which can use other use cases. So more or less just a list of the stakeholders, what stakeholders are related to what use cases, and the bounding box there means that what system these use cases will be using. For example, if we would have an ATM machine, we could have stakeholders like user or maintenance, and the use cases within the ATM machine would be something like withdraw money, see the transactions, load money into electronic card, and these sort of things. So it's more or less just a high-level description of things that happen. Of course, the use cases have their descriptions, their own documentation, but the use case diagram is the overview of how these different use cases are related. Finally, or one of the last diagrams is the communication diagram. It more or less shows how the things in what order things happen. So we have modules here, or the objects, and we are using customer on this example to set things in motion. Then the system exchanges messages, and like in this situation, when all these messages are sent, one package is sent for the customer. So the communication diagram shows how, in what order the different messages or activities within the system work. Similarly, the sequence diagram shows the same information, but on the more sequential notation, meaning that we start from the top and go downwards on the diagram, and the objects are sending each other information. Some of the objects may cease to exist at some point because they have done all the necessary things. But anyway, the sequence diagram depicts how these, in what order and how these different objects exchange information. So this is more or less usable to model the behavior, for example, between the server and client for the protocols and things like that. The one I skipped over was the interaction overview diagram, which is more or less the diagram of diagrams. It just shows how these different diagrams are connected to each other. It's a bit of a meta diagram. I know that it might be a bit, well, unnecessary even on some occasions, because there's also the package diagram. But anyway, this diagram allows to show that how different diagrams interact each other. For example, if there's separate use cases for failed activity and successful activity, then the diagram shows that these two different things exist. Finally, the timing diagram is simply used to do analysis on the processor loads and on how long it takes to send one message, for example, from sensor or heat sensor to the fire alarm or places like that, to ensure that there's always the processing capabilities to run real-time system or do analysis on how the messages are what sort of load the messages are causing for the system. So overall, the UML gives us 4 views: logical view, deployment, development view, process view, and physical view. The logical view, which is the class diagram, communications, sequence, state machine, and object, tell us what components will be made and how they will behave. So we can design the object-oriented structure, try to find and design things that have high cohesion and low coupling, so that we can get the different objects or components work independently and still do something relevant. The development view, component diagram, and package diagram, is the organization of assets, meaning that what belongs to what, because on one UML notation there might be something like hundreds of diagrams, so we need to have some sort of structure. The process view tells about how things happen, concurrency, synchronized aspects. For example, how customer or traveler, how they go to airport, leave their luggage, get their air tickets, go through the security gates, and how they board the plane when they arrive on the airport. And the physical view, the deployment diagram, tells us how things are physically set up. The +1 view, the last one, is the use case and the scenarios. That's not view about the system itself. It's the view about how what sort of activities the stakeholders have and how, for example, the system should be used to place a phone call, or how ATM machine should be used to withdraw money, or how the game should be used if we want to save our current status. These are more or less the definitions of making the design before the implementation or having documented features for your software. But one thing that you should keep in mind is that the UML is not development language, or it's not meant to be used so that every diagram is used every time. You can fill the library of Parliament House in Helsinki with the documentation from one larger software project if you would be doing all the UML design activities. So, of course, the idea is just to use those parts which are useful to you. There's no use in creating or maintaining useless information. But, for example, I have selected a couple of these UML diagrams which are more useful than others. For example, the use cases define how the system should operate. So that's something that is always useful, since it tells us how we should create the software, what sort of interface or what sort of user interface we should have and how it should behave. The class diagrams define how the internal parts should be defined so that our programmers have something to start up with. The deployment diagram defines the environment in which the system will operate, so we know what sort of hardware we have to get, or we know what sort of hardware we have to test so that we are certain that the system actually works. In addition, if we do client-server communications, we should have sequence diagrams, and if we are doing embedded system behavior, embedded system development, we should have state machines to define the behavior of the system. These are more or less the 5 diagrams which are extremely useful. The rest of them are more or less management aids or something that's useful but only in the project that has focus on certain activities. For example, if we are doing real-time systems, then we might want to do the timing charts, but if we don't have to worry about the responsiveness or things like that, when we are building satellites or Mars rovers or stuff like that, then we can just skip the timing diagram and you create, for example, define the use cases, draw a class diagram and get the deployment diagram done. So we have defined the behavior, the internal structure, and the environment the hardware needs for the final software. Those are at least the things we need to have. So overall, the idea of the UML is once again to allow us to have an idea on what the users need, what are the requirements, create the analytical architecture, and do the UML design on the first step here, so that we can actually create the components and the modules and the actual architecture which is imposed by the applied platform like mobile phones or laptops and stuff like that, and then write the source code, do the testing work, and have something that's deployable at the end. So UML is a tool to help you. It's not a system which is used to require you to do unnecessary documentation work. Like with the methods, the UML is not meant to be used so that you have to do everything that the book says you have to do. You take the parts that you find interesting or usable or necessary, use those, and can forget the rest of them. Okay, I think we are almost out of time, so I want to start with the requirements this week. I already put the next week's exercises online. As you may see, there's tasks revolving around drawing UML diagrams, and the rest of the first period exercises are used to learn about how to draw different things with the Argo UML, so that when the project 2 is introduced in the start of the second period, you have at least some practice and training on drawing class diagrams and sequence diagrams and activity diagrams and that sort of things, which are required in the second project. Okay, thank you.